Hello, everyone. I'm really happy to be able to talk to you about osmoregulation and ionic balance in shrimp, as they are very important to the success of salinity condition. If you look at average salinity, which is about 35 ppt, this is ions in the dissolved in water, which is chloride ions, sodium ions, which make the bulk, salt in the seawater. But you'll find significant quantities of sulfate, magnesium, calcium, and potassium, and just a few others, but very. If you're going to be farming near the coast in estuaries, then the salinity will drop below 15 ppt, and that means the mineral content of the seawater will be that much diluted. Typically, shrimp farming occurs under salinities fluctuating between 10 to 35 ppt. However, there's a lot of areas which farm shrimp under more extreme conditions. We have seen inland farming of shrimp. I can name a few areas in Asia, like in Andhra Pradesh, in India, or in the Mekong Delta and other areas where the salinity will be much lower, can be 0 to 5 ppt depending on the source of water, which can come from deep well, coastal rivers. That's one side of the extreme. The other side is high salinity, which you will find mostly in arid zones with high salinity seas, like in the Red Sea, deep by the Red Sea or the Arabic Gulf. But also you can find those in areas where coastal ponds have no due to biosecurity concern and during the dry weather, which can block to a certain extent the access to fresh water, to seawater. This happens in India on the east coast of Andhra Pradesh from April to July, and I have seen this, also experienced this in our farm in Lampung Research Farm, where during the dry month we would not be able to change water, and salinity would go up to 45 ppt within a few weeks. So what does this salinity changes mean in terms of osmotic pressure? Well, let's try to define a few terms. Like what osmosis is. It's a process by which water molecules through a semi-permeable membrane from a less concentrated solution into a more concentrated one. And the osmotic pressure would be the minimum pressure which you would need to apply to a solution so that you can prevent the inward flow of water across a semi-permeable membrane. It can also be defined as the measure of the tendency of the solution to take water in by osmosis. Let me explain through the graph on the right-hand side. I hope you can see my arrow. Here you have a U-shaped container with separate in the middle of at the bottom by a semi-permeable membrane, which can let small water molecules flow in, but not larger ions. Sodium ions flow back in the other direction. So what happens in this case? Salt was added to the left side of the container, so suddenly you have a much more concentrated solution on the left-hand side. Actually, the water molecules from the right-hand side are very attracted by those dissolved sodium and chlorine ions on the left-hand side, and they are going to migrate from right to left, attracted by these ions, and that leads to an increase in the water level on the left-hand side. Initially, the container, both sides at the same level of water, but after you add the salt over a few hours, you can see an increase in this level on the left-hand side. And the osmotic to bring on this surface heat that level back to the same level. That's what you see in the bottom right graph. So here pressure has been applied to bring back the level together at the same level. So that's the osmotic pressure. So typically, but it also can vary with water temperature. Typically, a higher temperature means there's more activity, more movement of the molecules and ions. So they will migrate. The water molecules will migrate a bit more actively. So water temperature increases osmotic pressure. Now, what does this mean for an organism or the cells within that organism? If you look at the bottom graph, you can see have been placed in three types of environment: isotonic, hypertonic with high salinity, or hypotonic with low salinity. So in isotonic, which is a normal environment, you have a balanced equilibrium between the inflow of water molecules and the outflow of water molecules from the cells. Place these cells into the hypotonic, suddenly the hypertonic environment on the left-hand side, the water molecule inside the cells are going to be very much attracted by the ions outside in the environment. So they are going to exit the cell, and if you place those same cells into a hypotonic environment with low salinity, it's the opposite happens. The water molecules from the hypotonic environment are very much attracted by the higher concentration of osmolyte inside the cells, and they will migrate into those cells, leading the cell to swell and to a certain after a certain stage to burst, and the cell will die. So obviously, this is not something that you want to have with your shrimp when you're transferring them to a different environment. So fortunately, shrimp are a euryhaline organism. That means they are organism that range of salinities, thanks to active osmoregulation. Here we define osmoregulation as the ability to maintain a constant osmotic pressure in the fluids by an organism through the control of water and concentrations of salt and other osmolytes. And shrimp, because they are able to osmoregulate very well, can maintain the hemolymph osmolality or osmotic pressure within a certain range at different salinities. So they're able to maintain, although the osmotic pressure changes in the environment, they maintain inside the shrimp at the relatively constant level. So the shrimp are such a good osmoregulator that even moderate salinity variations, just by 4 ppt, increases by 4 ppt or decreases by 4 ppt, as was done in the study on the right-hand side, do not affect the growth. In fact, that study found out that by increasing every 4 days and decreasing by 4 ppt the salinity, the shrimp grew better than the shrimp that were kept at a constant 30 ppt salinity. So as I mentioned, a shrimp can maintain the osmotic pressure quite constant. So the isoosmotic point for shrimp and most of the penate shrimp is around 25 ppt, depending on the research that has been done. That means the osmotic pressure that is inside the shrimp is the same as the one as 25 ppt salinity. So below 20 ppt or above 30 ppt, the shrimp will need to hyperregulate or hyporegulate the internal osmotic pressure to maintain it above or below the external osmotic pressure, so making a gradient. So you can see here at different salinities from 10 to 40 ppt, the different temperature from 20 to 32 degrees Celsius, the shrimp were able to maintain the osmotic pressure relatively constant, staying between 650 to about 800 of millimole per kilo. Whereas, if you think at 34 ppt and 16 ppt salinity, the osmotic pressure in 16 ppt salinity is less than half of the osmotic pressure at 34 ppt. So you would, if you had a balance, you would have seen a strong drop in osmotic pressure inside the hemolymph of the shrimp, which did not happen. And one organ in shrimp is key to this osmoregulation. It's the gills. They are the main organs for osmoregulation in shrimp because they have enzymatic system called the sodium pump or potassium ATPase, which is very active in the gills. And when you transfer shrimp to a different salinity, you will see an increase in the activity of this sodium pump. Other organs are involved in the antennal glands, which are the excretory organ of the shrimp, the gut, which will balance, reabsorb some ions from the nutrition, and the tegument. So here is what shrimp of different ages transfer suddenly to different salinity, from a normal salinity of 32 ppt where they were kept. So that study started from nuclei, working up to PS, and then juvenile and adult shrimp, and look what would be the survival of those shrimp if you transfer to different salinities ranging from 5 ppt to 60 ppt. So if you transfer them in the graph here on the bottom, in yellow with the halo, 32 ppt, the same salinity, there's no mortality, shrimp are okay. Actually, when you transfer them just to 45 ppt, 45 ppt is still survivable by most of the shrimp. But if you transfer them to 60 ppt, then all the larval stages and most of the PL stages will die. Even the juvenile shrimp and a small percentage of adults may die within 48 hours when you transfer them to 60 ppt. If you transfer them to lower salinity, you also see salinity, starting with 10 ppt and 5 ppt. Here you see at 5 ppt, all the larval stages died when they were transferred to 5 ppt, as well as the early PL stages, and most of the late PL stages also die. Have a bit of mortality, and those are pretty resistant. In fact, the salinity varies with the age of shrimp, as you can see from the study, and with the salinity. So let's try to look at what happens, in different farming conditions. Let's say if farming shrimp under low salinity conditions. The strategy for osmoregulation of the shrimp when they are placed in low salinity are multiple. First thing is they reduce the body surface permeability, salt and water, and so that the osmotic gradient is maintained across the body surface. So you will maintain the difference in osmotic pressure inside the shrimp and outside in the environment. They also produce more and more diluted urine in order to compensate for the passive inflow of water. Remember, you put shrimp, which has a lot of osmolyte inside, so the water molecules from outside will be attracted by those osmolytes. So all this water needs to be evacuated through urine. Also, they will absorb actively some salt and to compensate for the passive. And remember, shrimp can osmoregulate well, but especially with early stages, if you transfer them to a low salinity, suddenly you will obtain mortality. So the shrimp, when you change them to a low salinity, adapt. In the short term, what they're going to do is they're going to close the membrane pores, let's say the interstice cells in the epithelium of the gills, the gut, and the skin in general. So they will close those pores and reduce the permeability of the membranes. They will also increase the sodium pump activity, the sodium-potassium activity, which is a system that exchanges potassium ions against sodium ions. Finally, the shrimp will excrete ammonia, and this seems to have maybe a sparing effect on potassium. So instead of excreting the metabolite still needs, they excrete some ammonium ions, which are coming from the. To do this, this is an increase in strong increase in metabolic activity. There's a lot more oxygen consumption, of course. In the longer term, there will be some changes in the shrimp. For example, there's been observed a reduction in total hemocytes count, and also a lot of the immune response system are activity is reduced, like superoxidase, phenol oxidase, lysozyme activity will be reduced when you transfer them to low salinity. It has also been shown in the several studies that the shrimp become more sensitive to disease. For example, mortality of shrimp to white spot virus was demonstrated to increase when the shrimp were at 0 ppt compared to when they were challenged at 15 ppt. Similarly, when it comes to Vibrio infections, there has been shown an increased mortality of monodon larvae when they were exposed to the Vibrio compared to when they were exposed at 20 ppt salinity. So when a farmer is growing shrimp at low salinity, it will have observed mortality if they don't adapt the shrimp, especially the PLs at stocking, to progressively to a low salinity. What the shrimp risk is that the cells and the organs will suffer from hyperplasia. That means first swelling, then bursting. You will see a reduced growth. You have a high energy expenditure to pump the salts in the gills and the gut. And you have a passive loss of minerals that may lead to mineral deficiency. All this very active metabolism in the gills, in the gut, leads to oxidative stress and inflammation in the membranes that are osmoregulating. You will also see that because those membranes in the gills and the intestine and the hepatopancreas are and stressed, they will have lower efficiency, so you have impaired the respiration and impaired digestion. Finally, you have to remember you have a higher porosity and sensitivity of membranes to pathogens because the membranes are weakened. So that leads to reduced immunity and higher mortality from viral and bacterial infections. So what can the farmer do when they farm and shrimp at low salinity? One thing is to progressively adapt PLs when they're stocking them at lower salinity, but reducing salinity from nursery so that it gets close to the grow-out ponds. It's very important also to analyze the mineral content of the supply water. Typically, you will find that in low salinity water, you need to add minerals like potassium or magnesium, which will be deficient in the water. And Dr. Davis from Auburn University and his team have demonstrated that typically you want to keep salinity, the sodium to potassium ratio around 28 to 30. Similarly, you want to maintain magnesium above 50 ppm if you can. And also to minimize phosphorus fertilization so you can keep down the blue-green algae. So no need for to increase phosphorus in the water. Because the gills are more sensitive, you want to reduce ammonia by with the help of probiotics and UTAP products. And strong aeration is highly recommended, again, because you have a reduced oxygen transfer capacity of the gills. So the more oxygen in the water, the better the transfer. Frequent feeding will be also recommended. This helps keep the gut full of osmolytes to reduce the passive the losses by passive losses of minerals and nutrients. Also, frequent feeding allows you to deliver a constant supply of energy to meet the maintenance energy requirements due to high osmoregulation requirements. Finally, by doing this, you also on-farm solution to boost reduce risk of bacterial infection are also recommended. So that's what you can do at the farm, but at the feed mill level, what are the strategies that we could recommend? Well, first is boost mineral supplementation, especially focusing on potassium and magnesium, to a lower extent sodium, and then also some of the trace. Adding antioxidant to fight oxidative stress like vitamin C, vitamin E, organic selenium, zinc, and methionine, which is a precursor for glutathione. Optimize supplementation in the diet, so don't have too high a phosphorus level, but have enough so you have enough growth. Boost the gut health with organic acid and immunostimulants and herbal extract. and try to use antibacterials to reduce the pathogen aggression and improve the gut microbiota. Nutrition strategy for low salinity shrimp farming extend further, like formulating on digestible nutrient level, making sure you use high digestibility raw material. Remember, the gut may be weakened by this osmoregulation stress. So if you use a high digestible raw material, you have it's easier to digest. Similarly, using lysophospholipid and biosalts, which are emulsifiers, help improve the uptake of energy and improve the nutrient digestibility. We would tend to recommend using less inclusion of soybean, not exceed 40%, because the study showed that when you fed Vannamei with almost 44% of soybean meal, they had reduced antioxidant enzymes, higher malondialdehyde levels, and lower digestive enzyme activity, which so compared to 5% soybean meal, and that may be due to the inflammation of the caused by saponin has been observed in other species. It's recommended also to supply high levels of phospholipids so that you have a better gill membrane structure and gut lining. Finally, for the same reason, you want to supply enough omega-3 polyunsaturated fatty acids to have healthy membrane. For low salinity. So what happens when you farm shrimp under high salinity conditions? Well, having high salinity in the water means the concentration of minerals like sodium, calcium, magnesium, potassium, and chloride is higher. So that means maybe different needs of mineral supplementation compared to normal or low salinity. It also means, of course, you have a high osmoregulation stress. You also should remember that having higher salinity means it has an effect on other water quality parameters. They say higher salinity means higher alkalinity, so some buffering effect on the pH. You have also lower solubility of gas like oxygen and CO2, so less capability, less amount of dissolved oxygen in the water. You have reduced toxicity of ammonia, which is interesting. More halotolerant or halophilic bacteria, such as Vibrio. Vibrio can tolerate up to 50 or even 80 ppt salinity, depending on conditions. So if your salinity is high, there's a better chance you'll get more Vibrio in the pond and the gut of the shrimp. And furthermore, it seems that higher salinity can increase the virulence of some Vibrio bacteria like Vibrio harvii. So a higher risk of strategies when they are placed under high salinity. Well, remember, water is going to exit passively from the shrimp to the environment. So shrimp, to compensate for this loss of water, drinks a lot of water and excretes a lot of minerals to maintain the osmotic pressure inside through intensified activity of the sodium potassium ATPase, especially in the gills, but in all the membranes exposed to the high salinity. If you did not do that, you would have accumulation of salt inside the cell, which would lead to cell hyperplasia and inactivation of the metabolic enzyme. So in order to avoid this, shrimp use small water-soluble molecules like free amino acids, betaine, taurine, to help maintain osmolality inside the cells without harming the metabolism. The salt content inside the shrimp, the enzyme activity goes down. But those which are biologically useful and involved in the metabolism do not affect the enzyme in the metabolic enzyme in the same manner. There was a very interesting study published earlier this year that showed the important role of, like betaine in this situation. But overall, osmolyte, like free amino protein that you find in the molar lymph, I mean peptides and protein molecules, help increase the osmotic pressure inside the lymph, but the hemolymph, but without affecting the metabolism. Also, studies has shown that if you place shrimp at very high salinity, like 55 ppt, and analyze the total free amino acid in the abdomen, you will find higher levels in those shrimp compared to those kept at only 20 ppt salinity. And in that study, they found that it was mostly the levels of protein and glycine that went up. One amine is very important. It's glycine betaine, and this recent study this year published this year showed that when shrimp are fed at a regular diet and placed at high salinity, you have synthesis of glycine betaine and reduced ammonia excretion. So this was observed just on the short period of 7 days when the shrimp were maintained at high salinity, different salinity condition. So you see on the graph, you have a reduction of the ammonia dissolved in water, which reflects the reduction in excretion. At the same time, this synthesis activity for betaine. So the glycine betaine, also known as betaine or trimethylglycine, is synthesized in the hepatopancreas and in the gills. So there you can see when the salinity goes up, the rate of synthesis goes up in both organs, and that translates later on over time with higher accumulation of this betaine in the various organs, not just, of course, the hepatopancreas and the gills, which was synthesized, but also the muscle and the hemolymph. So the shrimp are able to change the protein catabolism from the excretion of ammonia to using this ammonia used for to produce more betaine, which they produce from choline. So all things happening when you have shrimp in a high salinity. Remember, the permeability of cell membranes varies with the salinity and can slow down the migration of ions through the osmotic gradients. So that's one way of protecting. Also, some lipids seem to play a very important role in this permeability, like phospholipid and omega-3 fatty acids. You know that most marine fish and animals have high levels of omega-3 fatty acids compared to freshwater fish, where you have more omega-6. To the and the role in the membrane of the cells. So it has been shown that in the gills of shrimp kept at 30 ppt salinity, the phosphatidylate content of the gills was higher. But on the other hand, if you look at other lipids in the gills of shrimp kept at 3 ppt, you had higher level of triglycerides, phosphatidylinositol, and phosphatidic acid. Similarly, in the hemolymph, the study found that at 30 ppt, you had higher levels of HDL lipoproteins than at 3 ppt. Interestingly, at 3 ppt, the 18 omega-3 fatty acids, just 18, not EPA, DHA, but 18 omega-3 fatty acids were higher at 3 ppt salinity than at 30 ppt salinity. So what happens again under high salinity conditions? You have a higher incidence of Vibrio at high salinity compared to low salinity, and higher virulence of hypersaline conditions. And a study by Sullivan in 2012 showed that you had a higher severity of Vibrio alveolar infection of Vannamei when they were kept at 35 ppt compared to those kept at 5 ppt. Similarly, in Vannamei, kept at 55 ppt died, or kept at 5 ppt died faster than those kept at the normal salinity of 28 or 34 ppt. HHNV tends to reduce growth, but the growth reduction is further aggravated when shrimp are kept at higher salinity. What can farmers do? at the level to fight this against this high salinity. First of all, I mean, it's very important to have very high oxygenation due to the stress to the gills, and the reduced oxygen solubility in high salinity water. So very strong aeration is important. You want to minimize fertilization because you have a lot of minerals. You want also to, when you can, and if the biosecurity conditions allow it, you want to change some water to refreshen the water quality. Continuous feeding again is recommended because it allows you to give a constant supply of energy and mineral in the water. Overfeeding, and again using tools like UK extract or probiotics to reduce total ammonia nitrogen is recommended, as well as on-farm usage of antibacterial and probiotics to reduce the virulence and the density of Vibrio. At the feed meal level, what can you do? Well, remember this, you have a high energy and high protein requirement, so you want to increase those levels to meet the increased energy requirement from osmoregulation and to build up the pool of free amino acids inside the emollient to have a better, higher concentration of osmolyte in the emollient. Emulsifiers like lysophospholipid or bile salts can improve the absorption and the mobilization of fats and energy to get a better health and a better energy utilization. Using high digestibility raw materials and nutrients to avoid stressing the gut, and using digestive aids like emulsifier and enzymes like lysophospholipid, bile salts will help, as well as using high levels of antioxidant to fight the oxidative stress from higher activity of sodium pump. High levels of choline would be suggested to boost the production of betaine glycine, and I would recommend to add high level of phospholipids and omega-3 fatty acids so that you have a healthy cell membrane. I would also advise against using excessive levels of soybean meal and other plant proteins with anti-nutrient and inflammation agents that could affect the health of the gut lining. Finally, applying antibacterial phytogenics and organic acids to boost the gut health and to help the ability of the shrimp to resist Vibrio is recommended. So that was in a few slides what I could say about osmoregulation. And I would like to remember that both low and high salinity cause a strong osmoregulation challenge and stress to the shrimp, especially in the most exposed organs, which are the gills, the gut, and the hepatopancreas that you want to support. So this results in oxidative stress and specific nutritional requirements, which can be addressed by nutritional strategies such as supplying appropriate levels of osmolytes, adapting mineral supplementation based on the energy and the proteins supply based on the salinity that you're farming, and boosting the functionality of cell membrane by optimizing lipid nutrition with the help of omega-3 fatty acid, phospholipid, and even emulsifiers, so you have a better use of your omega-3 fatty acids inside the body. Improving fat and energy absorption and mobilization through the use of digestive and metabolic enhancer like those lysophospholipid and bile salts I mentioned. Again, fighting oxidative stress with dietary antioxidant, selenium, zinc, methionine, helping shrimp withstand higher risk of disease challenges by optimizing the gut health and optimizing the immune status by using health-promoting additives like organic acid, phytoenergic, or other immunostimulants. Finally, I'd like just to remind you the main difference between farming under low and high salinity. At low salinity, it's important to look carefully at your mineral supplementation, and usually you need to supplement magnesium and potassium in diet. At high salinity, You have lower ammonia excretion due to betaine synthesis, so choline supplementation is important. But you have higher virulence of Vibrio, so utilizing additive strategy against Vibrio is quite recommended. All for today, and I look forward to your questions.